Welcome back to the PyTorch series of tutorials. So in this lab we are going to build audio classification example, through Google Colab as well, and we are going to use this dataset, Quran Recitations for audio classification. So this is a set of audiobooks, it's a set of audio files for different recitations by different people for the Quran. Quran is the holy book of Islam religion. So we are going to use this data set, and it consists of multiple wave files, as you can see here, and the class, which have multiple people who have these recitations. So we are going to start first by downloading our dataset. So we have started a Colab file. We have connected to GPU, T4 Tesla GPU, because we are going to need a GPU definitely here. So now we can start by downloading our dataset. So we are going to do as usual part, which is pip install open datasets, and then we are going to import it. Import open datasets as OD, and then od.download, and we are going to take this, the link of this data, put it here, and now it will ask for the password. So let me copy it. I already created a video. I'll put it in the description on how to download the dataset directly from Kaggle. So I'll write my username and the key or the password, and the dataset is downloading. So this is gonna take a few seconds. Okay, great. Now we have our dataset downloaded. Now we can start doing our imports. So first of all, we are going to import Torch, obviously, and then we are going to take from Torch import NN for the neural network layers, and we're going also to use torch.optim import Adam as our optimizer. We're going to import Libruza. This is a library that will be used for audio processing. We are going also to need some other stuff from Torch as well. So from torch.utils.data import dataset and data loader. We are going also to import from sklearn.preprocessing import label encoder, because we are going to need this for encoding the classes because they are strings. Import matplot library .pyplot as PLT. We can use this for visualizations. We are going also to import pandas as PD, and we are going to import numpy as NP. These are some basic stuff. We are going also to import OS. We are going to import time as well, and finally we are going to import this from skimage.transform import resize, and we will see how we will use this. And I believe that's all. Let's set also the device. These are things that we do every lab, so or every tutorial. We need to do our imports and to set the device to CUDA, and we'll set it only if torch.cuda.is available, and if this is false, which is else, then we are going to follow the CPU. Now you can put here MPS if you have a Mac, and it will use automatically the Mac GPU. Also, one more thing to mention, that as usual, the lab is attached in the description. You can find the tutorial notebook on GitHub in the description with comments and explanations. All right, so now we have all our imports, no need to do any installations, everything seems fine, and we already have our own data set here, Quran Recitations for audio classification. We have the file path.csv and the data set, which contains all the audio files. If it's not opening immediately like that, then it means that it have a lot of files inside. And if you open this one, you have all the people here, all the people that recited the Quran, so that we will be doing the classification among them. So you can open any audio file, listen to it. They are, I'm not sure how many they are. I think they are 10 if I'm not mistaken, but we can check that through Python. Okay, so let's read the file path, and I think it will have all the information. So let's write data underscore data frame, or df, is equal to pd.read csv, and we can copy the path of that one and paste it here. Now we have the data frame that contains all the details of the data set. So I think everything is fine now. So it contains the path. Usually the audio files, you need to build this thing. So we are lucky because this data set is already prepared in a good way for us. We can access it directly, easily with this data frame. And we can also check how many classes do we have. So we can write data underscore df print, sorry, I forgot the print, data underscore df of class dot unique, and we will see how many we'll see the classes, okay, and we want also how many of them. So we can copy them, we can put an extra line here, and then we can paste this and put len of the same thing, of only this thing. Now we have 12 classes, and these are our classes. The path of each file is already in the file path column, so no need to worry about the path. And I think everything is fine. But there is one thing to mention. This path, there is a dot in the beginning, which means that we need to edit this path to match our local path, or the path that we are working on. So this means that this path is starting only from the dataset that we are having. It doesn't contain the path of your files here. So what is the path of our files? So the path of our files is starting from the word dataset, which is this one, and this one also. So we will need to edit it, okay? So we will need to put the dataset path behind this one, okay? So to have the full path here. So we will just copy the this one, copy the path of this one, and we will edit it. Okay, so how can we edit this one? So it's very easy. So data underscore df of file path is equal to our original path plus the same thing, data frame of file path. Okay. Now we need to replace the dot, so we need to remove this one. So we are going to put it str of 1 till end. Now let's print head to see how it looks like now, because now it will be clear since you will have both tables. Yes, now I think it will be clear now. So you have here, it's starting from dataset, and here it's starting from content. So which means that here you have the full path of the data, okay? So let's try to get only maybe like the first one or something, because it will be more clear. So like that, and I'm not sure, not that way. So it should be by .iloc of 2. This is the path. Now this is the path, as I mentioned, it's a complete path. So let's delete this one and let's continue our work. Now we can investigate more on the data if you want. So we can see the data shapes. So let's print some data analysis here. data shape is data underscore df dot shape, and print the also class distribution. So we already have this one, but we will want to print the class distribution. So let's write here class distribution, and this is going to be data underscore df of class dot value counts. And let's see here what we have. So the data set is not completely balanced, but we can say it's kind of acceptable here, because I think we can visualize it to see more. So let's try to visualize this. So let's keep like a line, an empty line here, and then we can write, we can create a plot here. So the plot, we can have it 8 by 8 maybe, and then plot should take fig size equal 8 by 8, and then we can have plt.py class counts, which is this one, and also we can give it also the labels as class underscore counts dot index. I think we're gonna need this one, not class counts dot index, and we're going to set some numeric auto pct, this one, and we're going to give it like that, so that we can have the numbers in a proper way. And then we will put plot dot title of class distribution, and then we will plot dot show. Let's see what we will get. So yes, perfect. Now we can see the data distribution here. So it's like I'll not say 100% balanced, but it's somehow acceptable. Still, there are some techniques that we can balance this by doing some data augmentation maybe, or some other techniques we can do. But we will, for this lecture, we will proceed with this data, with this amount of data. Okay. Now let's start doing the data split. The data split part is where we will split our data into training, testing, and validation. So, or for making it more clear and in order, it will be train, validation, test. So let's start by making our train data, which is df dot or data underscore df dot sample. We are going to take a sample of the data for 70%, and we are going to set random state as 7. Then we are going to do the test dot sample. So we are going to take the testing as the part, not dot sample, sorry, dot drop. So I have already explained this in the previous tutorials, but just like explaining it again quickly. What we are doing here is that we are taking a sample of the data for 70%, and the rest is we are going to drop it. So the other 30% we are going to drop it, and then we will have the 30% for testing. Then we are going to do the same but with testing data, because we have, the plan is to make 70% training, 15 validation, 15 testing. So validation test dot sample, and we are going to take a sample from the test. So we need to write here frac equal, and we are going also to write here fraction equal 0.5, because we are it's a 30% already, so splitting it to 0.5 will be 15%, 15%. And random state is 7 also. And then we will take the rest, which will be test dot drop We are going to drop from the testing data the ones we took for validation. Val.index. Now it makes sense, I believe. And we are going now to visualize our data. So print train shape. Now let's see the shape of our data. And this is going to be train.shape. Let's copy this and put val.shape and test.shape, and here val, here test. Now let's see how it will look like. Great. So this is our data. So it's 70%, 15, 15. Now it makes sense. Now we can proceed because the total amount of the data we have is 6,687 audio files. All right, great. Now I think everything looks good. Now let's start going a little bit deeper and start creating our label encoder and the custom datasets. All right, so then we are going to start by having the label encoder first, because we need to change these into classes. So these names need to be encoded into numbers. Okay. Now let's try label encoder is equal to label encoder, and so we created an encoder instance, and then we will have class custom audio dataset. We are going to create this custom audio class. Now it will contain everything related to data processing. So it will be like before, but we will have one more function to process the audio file. Okay. Now let's first start by having the construction. So def initialize, and we will have self and the data frame. As we mentioned, it will get a data frame because we already have the data path and everything inside the data frame. So we will read from the data frame first. Now we'll create self.dataframe is equal to data frame, and self.labels is equal to torch.tensor. Now we are going to use our encoder, and it will be .fit transform, and inside the brackets we're going to put data frame of its like these brackets, and it will take class, and then we are going to make it give it a certain type of torch dot long tensor, and then we are going to move it to our device, which is the GPU. Okay, great. After that, what we're going to do is we are going to read our audio path. So self.audios is equal to a list of torch.tensor for self.get. This is the part that we will add more. Spectrogram for a certain path, and we are going to write here, set it as a type, torch.float tensor, and then we are going to write for path in our data frame file path. Okay, now what did I do here exactly? I made it a loop, okay, because we need a loop because we want to get the spectrograms of all the audio files or all the wave files that we are having. So get spectrogram function, I used get spectrogram function that we are going to implement just after a moment, and we have converted it into tensor, and the type of that tensor is a float tensor for each path inside all the paths that we are having inside the data frame. Okay, now feel free to ask any questions in the comments, because I know this may seem a little bit complex, but take a while to read it. It makes sense, and hold on until we finish the whole class. It will be completed. Now we are going to have the pre-reset function len. We are going to edit this one, and we are going to return self.dataframe.shape of 0. Then we are going to write get item get item underscore, and this takes self and index. Now when we start this one, it will take image path is equal to self.dataframe.iloc. This is used to get a specific path and label with an index. Okay, so let's say you put here 2, it will get the second file path and its corresponding label. For index, 0, because this is the image path. And then for the label, we are going to get torch.tensor self.labels of index dot to device, and we are going also to write the audio. So now we got the label as well, and we are going to need the audio. So not only the path, but the audio itself, which means the audio itself by the index, okay? Which means the spectrogram file or the audio with its own features, not only the path of the audio. So we are going to write self.audios of index dot unsqueeze, so that we can have a proper shape of 0 dot to device. Then we are going to return audio comma label, and we can also return the image path if we want, but we will use only these two because get item function is used. This function is automatically used with this name by PyTorch and during the training, so it will only require the inputs and the outputs. It will not require the image path, so we can always return only the inputs and the outputs. Okay, great. Now comes the interesting function, which is called get spectrogram. Now get spectrogram is a function that that helps us get the audio features. So you know that each file we use takes usually each data we use in deep learning has its own features. For example, if we have text files, we'll see this in the next lab, but we need to convert these text files into numbers so that it can make sense to the model and we can feed it to the model. Same applies to images, and same applies to audio files as well. Audio files are the most, in my opinion, are the most I'll not say complicated, but tricky part. So let's see how we can implement this. So there are a lot of things in a lot of ways to extract features from audio files. In this lab, in this tutorial, we're going to get the spectrogram. So we're going to set a sample rate as 22,050. 22,050. It takes file path, by the way, okay, which is the audio path. And we're going also to set a duration, assuming that each audio file is 5 seconds, okay? We are going also to set the image height is equal to 128 and image width is equal to 256. So let's not keep so many spaces. And as I mentioned, again, you'll find this notebook on GitHub in a link attached in the description, having comments and explanations. So feel free to check it out. We will also need to load the audio file. So first of all, we will load the audio file, and librusa.load load from the file path and take the sample rate that we mentioned and duration that we mentioned. Now we read the audio file. We can use the signal directly, but it's better that we extract the spectrogram from it because it will contain more details and more data. So the spectrogram will be something like this. So something like that from Wikipedia. You can think of it as the representation of the audio file. not just a set of numbers, but it will be something like an image containing numbers. These numbers represent the image. The x-axis represents the time, and the frequency is represented by hertz or kilohertz in this case. The frequency is represented by colors, as you can see. For each specific time, it has different colors, and the color intensity represents the frequency. Okay. Now let's get back to our function. Now, after we create the after we read the file, we will create the spectrogram. We will use also Librusa. It's easy. It's not an issue. And .librusa.feature. So we have here a lot of features, as I mentioned, and we can take the MEL spectrogram. So I think yes, that's the one. And we will use Y as our own signal, and also we will give it our sample rate. SR is equal to SR. We're going also to give it some parameters that you can play with, like this one, the FFT. And we are going also, you can have read some description of each parameter here. So these are the configurations that I found after some research on the internet that seems to be the best. Hop length is equal to 512, and number of MELs is 128. So we have got the spectrogram. Now we will need to convert it into dB or decibel, as the dB contain more details of audio files, so that it will allow the model to learn easily and find more features to learn from. So power to dB. So we are converting from power to decibel, or from the old MEL spectrogram to dB. And we are going to give it spec. And we are going also to give it np.max. Now we finally was able to get the audiophile features. What we are going to do now is to resize it. Okay, so spec resized is equal to change the size so that it can have all of them have a proper size that is matching both the duration with the sample rate. So let's see how we can do that. Librusa.util.fix length. We are going to make the length fixed for all of the data that we are having, because we need any AI model or any deep learning model needs a constant length. Okay, size is equal to duration, and duration multiplied by sample rate, and these two, let's put them inside brackets, and these are divided by 512 plus 1. This is the new size that we are having, and we are going to do one more operation, which is resize. Now we will resize that using the specs that we created with image height and image width, which are these things that we got here. And we are going also to use anti-aliasing is true. Then we will return spec resized. Let's run this. So we don't have an issue so far, but we don't have a syntax issue, but let's see if everything makes sense. So we will create a train dataset is equal to custom audio dataset, and it takes the data frame of train. Okay. Train df, which is that one. One thing, guys, there is not a mistake, but something that we can fix here for more consistent output is that we create the label.fit transform data class we can create this outside. Okay, so instead of creating this here, we can put it outside so that we can have all the labels here. But this will this will help us making the output more consistent. So let's do one thing. When we create the label encoder, it's better that we change inside the dataset as well. So instead of having this here, we can put it before the split so that we can have a consistent output. So we can change the output before we split the data so that we can have everything set and make sense. Data underscore df for class with label encoder, and we can change this here so that we can have the class already converted into numbers or encoded into numbers before we do anything here. And here, instead of having the data of data df of class, we'll put the data frame of class, but without converting or encoding it because it's already encoded. So let's run this again, and maybe we can verify that we have a proper output. So we can only see data df here. So it's converted already. Great. Now we can proceed, and we can create here our dataset, train dataset, and test dataset, and and validation. So val, and here we're gonna put val. Here we're gonna put test. We're gonna put also here test. Now let's see if everything is working fine. So if this takes few moments with you, it's okay, no problem. This is because these are audio files, and during the initialization, we are getting the specs as well. Okay, so we are getting the features of the audio file. So for each audio file, or out of this one, 4,600 and 1,000 and 1,000, for each one of them, we are doing the get spectrogram function. So this is gonna take a while, so it's okay. It's not an issue. I'll continue the video when this is done. So let's give it a moment, and I'll continue the video when this is done. So we got an error here. Couldn't determine the shape of object type series. So I think we are having an issue here. So what is val? It's getting the error here in this part in labels. We are having an issue here, which is strange. So let's try to copy this one and solve this issue. Let's see what is the problem exactly. So this is val, and let's see if it's converting it or not. We are getting the error, but I'm not sure where. So val of class couldn't determine the shape of object type series. Because this is a series, not a data frame, which means that we can provide it as a list, and I think it will be solved. Yes, we should provide this as a list. So we can put this as a list here like that, and then it will work. So let's give it a few more moments to be solved. Okay, so it's done. Now let's get back to work. So we are going now to set some hyperparameters because we are going to build the interesting part here. So the first thing we are going to set is the learning rate to 1e minus 4. Then we are going to set the batch size, which is going to be 16. And then we are going to set the epochs to 25. Okay, and I think that's enough. So we are going also to proceed train loader. We are going to create data loader so that we can iterate through the batches, train underscore dataset, and we're going to give it a batch size of our batch size. We are going also to use shuffle as true, and we're going to copy paste this for the val and the test. We're going also to write here val and here test. Great. Now the model, the part related to the model. So since we have converted it to spectrogram, and spectrogram contains somehow image structure, so we are going to build a CNN, okay, a convolution network, but it only has one channel. Okay, so the model will be a little bit big, and let's try to make things simple as much as we can. So we create a class, and we'll call it net, maybe, yeah, as for network, and it inherits from NN module. Now we create, we'll create the instructor super, because it inherits. So let's write, I don't know what happened, yeah, dot underscore init or initialize. Then we're going to define our first convolution, which is nn.conv2d. It only takes one channel as mentioned, so 1 and 16 filters. The kernel size is going to be 3 and padding is 1. Then we're going to put the second convolution layer, so nn.conv, same thing, 2d, takes 16 channels, because it will give us here, the output will be 16, number of input channels and the number of output channels. Okay, so this is the number of output channels, excuse me for any confusion. Then this will give us 32 channels, and it will give us the kernel size will be also 3, and we can set as well padding as 1. We are going also to get the conv3, which is conv2d, but this takes input 32 and produce 64 output channels, and the rest of the settings is the same. We're going also to have a pooling. The pooling can be only one because it doesn't need any shaping, so it will be max pool 2d 2 by 2. It returns the same shape, so we are going to use the same pooling for all layers. And we are going also to put a ReLU activation function. So nn.ReLU, I think yes, like that. And then we are going to write the flatten. After the convolution stuff, we will need the flatten part. So nn.flatten. Then we're going to write self.linear 1 as nn.linear. So now we are going to write the sizes of each one. So it will be 64 multiplied by 16 and multiplied by 32, and the output of the flatten will be 4096. You can try to play with these numbers, of course. These I got them from here, the output of each layer, and already explained in previous lectures as well. So the second linear part is going to be linear 2, and this will be nn.linear for takes input 4096 and gives the output smaller output, because now we want to start reducing stuff. Self.linear of 3 is equal to nn.linear for what now? For 1024, and gives us maybe 512. And self.output is equal to nn.linear for 512 input, and the output will be the length of the data underscore df of class dot unique. Now you can change this and write 12, but I prefer to write it this way so that if you change the data set, this can update automatically. It's more professional. Now we can write also a dropout layer that we can put between our network, and n.dropout, and set the dropout by 0.5. Great. Now we have created the layers. Now we will create the forward function. Okay, so forward, and this takes self and x. This is how, here in the forward function, we will see how the data goes inside the network, okay, or how the forward propagation happens inside the network, okay? Okay, great. Now, first of all, x is equal to self.conv1d of x. X is equal to self.pooling of x. Then we will have also the second conv. So, self.conv2d for x, and x is equal self.conv, again of x. This is conv1 pooling, conv2 pooling, and we're going to do the same for conv1 to 3 without d. Suppose not d, this is the confusion. Okay, and then after we have done the convolution parts, then we can give it a ReLU. So x is self.ReLU for x. Then that's it. That's the convolution part. Now we will flatten our things. Sorry, our output. But before we do the flatten, we will change the view. Okay, so we will reshape the data to make it matching the flatten. X.view of x.size of 0 by -1, and then we will continue the flatten part normally, self.flatten of x, and then x equal self.linear of linear 1 of x, x equals self.drop out of x, put a drop out, then we will put another set of linear and a drop out, but the second linear, here we'll change it to the second linear, and we will have linear 1, 2, 3, so we'll put the linear 3 as well, and we then can put the output, self.output x, and then we are going to return x. Now we have created the network, so or the network class. We have an error here, an n.module, so there is something wrong here. So I'm not sure why this is happening, but n.module. Okay, it should be capital letter, I think. Yes, that's the issue. Okay, great. Now we will create the model. So our model will be net dot to device, because as you know, and as mentioned in the previous lectures, PyTorch, you need always to make sure that you need to transfer manually everything to device. And device here, I mean the CUDA or the GPU that you have. Okay, great. That's the model. We can give it some like good looking from Torch summary, import summary, and we can see our model by giving it a sample output. So model, and the output is by 128 and 256. Let's try to see the model, and here you go. The model is you can see the model here with some like good view, and I think everything is fine now. For your information, the total trainable parameters or total parameters are 138 million parameters, and the model takes around 10 megabytes. for doing the inference or the forward propagation, and the total size is around 500, almost 540 megabyte. Okay, great. These information are not important to us for at this stage. We only know that it's 138 million parameters, which means it will take some time to train. So let's see what will happen. Now we will create the loss function. So it will be an n.cross entropy loss because it's a multi-class. And then we are going to create the optimizer as Adam optimizer. So model.parameters, and we are going to give it the learning rate as our learning rate that we have created, and that's it. So let's see how it will perform. Great. Now it took 4 seconds, no issues, everything seems fine. Now the interesting part, the training part or the training loop. Now, I'm always, during this series of tutorials, I'm following the same template or the same structure of writing the code as much as I can. So, as usual, we'll create the lists, the empty lists, total loss, train. These are for plot, so we'll write plot here, and total loss validation plot. Then we will write also total accuracy train plot, and we are going to write also total accuracy validation plot. We are going to fill these lists inside the training loop, and we are going to use them later to plot the training progress and see if there is any sort of overfitting. Okay, for epoch, in epochs or in range epochs that we have created here, 25 epochs. So for epoch in range epochs, we are going to start to create our own variables. So total accuracy train is equal to 0. Total accuracy for this epoch, I mean, total loss train is equal to 0. Total loss validation is equal to 0, and total accuracy validation is equal to 0. Okay, great. Now we are going to loop through the data inside the batch that we are having. So for each epoch, and then we are going to get through the data inside, because for each epoch we loop through the batches, and then for each batch we loop through the data. So now we loop through the data inside the batch. For inputs, comma labels in train underscore loader. Outputs is equal to model of inputs. Train underscore loss is equal to the loss criteria that we created. So we are going to get the loss of the model, so it's input, not inputs, and criteria. So for outputs, comma labels, so we are going to compare the output of the model with the original labels that we are having. And then we are going to calculate the loss. So total underscore loss underscore train is plus equal train underscore loss dot item. Then we are going to do the backward propagation. Backward. Now everything is same as previous labs. Then we are going to calculate the accuracy. Same way. Train is torch dot arg max. For outputs, comma axis is 1, equal labels dot, this should be inside the brackets, labels dot sum. Now what I'm doing here, I'll explain this again. Actually, what we are doing here is that we are getting the maximum, the torch argmax for outputs is equal to labels. So which we are getting like an array that is saying to us which labels are correct and which labels are wrong. And then dot sum between the outputs and the labels, or the outputs of the model and the labels. And then dot sum means to calculate the sum of the sum of the correct numbers. Okay, dot item to get it as an exact number. Now, what we will be doing here after that, we will be doing total underscore accuracy underscore train is plus equal train underscore accuracy. Then we this is to get the accuracy of the epoch, which should be improved after each epoch. Optimizer dot step, and then we are going to reset the optimizer dot 0 grad. Then we are going to do the validation. So with torch dot no grade or gradient, this is for inference or to do the validation. For inputs, we're going to do the same. For input comma labels in val loader, this is for validation data. We are going to have outputs is equal to model of inputs, so it's same, but the only difference is that it's on validation data. And we are going also to calculate the loss, so val loss is equal to iteration of outputs comma labels. And then we're going to have total loss val is plus equal val underscore loss dot item. Everything is same. The only thing is that we are not going to do the backward propagation, and we are not going to touch the optimizer during the validation part. Val underscore accuracy is equal to same thing. So we can copy it from here for faster writing of the code, and then we can also copy this from here, but no, this is for training, so we can write here total accuracy validation is plus equal to val underscore accuracy. It's a bit confusing, so if you don't fully understand it, go to the notebook in the description, take your time reading it. You can digest it easily, but don't panic, it's very easy. And if you don't understand anything, just write in the comments what you don't understand. Now we are done with the training. We need to fill these lists, okay? So that will help us inside the plotting. So the lists are filled after each epoch, so they will be filled on the first loop level, okay? So total underscore loss underscore train plot dot append. So we are going to append here the rounded loss total underscore loss underscore train multiplied by 1000, and we're gonna round it to 4. Wait, this round should be inside. Yes, that's it. And we are going to copy paste this for validation. So instead of train, we'll write val, and here we are also going to write val. Total loss val plot, total loss, it's called validation plot. And this total loss val. Okay? And follows the same procedure. Then we are going to plot the total accuracy train dot append. This will be also round of what? Now this will be of total underscore accuracy underscore train. That's the one. Not multiplied, but it will be divided by, because we need it as a percentage. So it will be divided by train dot dataset. Train underscore dataset dot underscore underscore length. So it will be divided by the total amount. So the total data that was classified correct divided by the total data that we are having multiplied by 1000, and this is to get the by 100 to get the percentage. Okay, and we are going to round this to 4 as well, and yeah, that's all. Now we are going to copy paste this, but for validation. So instead of train, we will write here validation, and instead of total accuracy train, it will be total accuracy val, like here, like that. Great. Now we're done. The only missing part is to put some print, okay? And we can also put time or a timer that can give us how long did the training took. But let's first write the training part. So let's write f and epoch print. This is epoch here, like that, for which epoch is it training now, and we can put slash number of epochs, number of epochs. The train loss is how much? Now the train loss, we can put it here, round, for total underscore loss underscore train divided by 1000, or divided by 100 better. Can put this inside, divide by 100, and we will round it into only 4 digits. Okay, so we can also write the val, I think the brackets has confused, val or validation, or no, first train loss, then train accuracy. Then the train accuracy is going to be also the same here, but not that one, sorry. It will be the same as we already have it here, total accuracy train, which is that one. So it will be this part, total accuracy train for that epoch. It will be the whole part of that one. So you can copy paste it easily. And then after that, we can write the loss, the train loss, train accuracy. Then we can write the validation. Loss is going to be same like this one, but we will only write the val here, total loss train, so it will be total loss validation. And then we write a comma here. Let's make our prints organized. We will write validation accuracy, and this will be like this, but we will only change also the variable. Instead of total accuracy train, it will be total accuracy. Wait, what happened? Okay, typo. Total accuracy val, okay, and divide by validation dataset. This should be validation divided by val dataset. That's a mistake. Okay, now that's all. We can print also a line, an extra line here, to make sure that between each epoch, or we can make it more fancy like that. So can print 30 equal signs between each epoch. And we can also put a timer to know when did the epochs started. So we can import up here time, or we can import it down, no problem. We can import time, and after we import time, we can write start time is equal to time dot time, and we can start from here. And after the training is done, here print training time is, and we can write here time dot time minus start time. We can put it also rounded, so we can round this to maybe 4 values, and we can put this inside brackets, and we can put here seconds. That's all. Let's see if it's going well. Let's try to run the training loop. So this is gonna take a while, but let's make sure first that the first epoch is working, and then we are going to stop the video and continue when it's done. So so far, oh, okay, tuple doesn't define round method. Okay, so seems there is an issue with round. I think this should be this is a typo, I believe. So round total loss train is so let's see what is total loss train here. Now total loss train is a number, and if we write this one like that, what we will get this without any problems. So something is okay. Let's copy the whole print and try to solve it here. I think there is a mistake somewhere, but I'm not sure where. So let's try to check where is the issue. So round here ends up, I think this round is having an issue. So round, okay, that's the problem. Okay, so we should put this inside, not outside. So that's the problem. Let's try to see again. Okay, I think I'm making the same issue somewhere. Here also. No, not here. Here is fine, but here in train accuracy, we should put this inside the brackets. Now it will work. No, still same issue is happening somewhere else. So validation is here, and so we have defined this bracket. The end of it is here. Yeah, I think the issue is maybe this will be solving the problem. Now let's try solving it in the back as well. It's extra tuple, so maybe that's the reason. Okay, round takes at most 2, but 3 were given. So I think we need to put these to separate these. So it seems there is a typo. Okay, not sure where is the typo, but this is not helping. So let's try this way now. Round tuple doesn't define round method. Okay, now let's try to print it in a different way. Okay, now let's create, this is the make it epoch string. Okay, I'm debugging the issue with you guys, so bear with me please. And we can close the brackets that way, and we can create it in a separate line. So this is the first epoch. I think this way will be more organized. And the train accuracy, the validation loss, the validation accuracy, and close the string. And now we can try to print it. I think now it will give us where is the issue is exactly. Epoch string. Oh, sorry. Okay. Now the epoch is in this one. Okay, that's the problem. The issue is in this one. That's the problem. So we are going to do round for okay, that's a comma. This should be a division. Okay, and now it will work. Okay, let's better make it this way. The printing is more organized this way. And let's put the indentation, and let's run again. So let's see if everything going good. Let's delete this cell because it's no longer needed. And let's see if everything is good. We can check also the utilization of the GPU RAM. So it seems good. No problems. Can increase the number of batch size if you want. And everything is good. So it started already the first epoch. And the only issue is that we need to add 1 because it's starting from epoch 0, not 1. But we can make this modification also. So let's interrupt and let's make epoch out of epoch plus 1, oh sorry, epoch plus 1, and let's run again. It's just for making things consistent while printing, but this is not necessary. It will not block anything. So let's see if everything is going fine. Okay, so we are in the last epoch now. The training took 500 seconds. Okay, so looks good, but we have one issue here. That the training accuracy already started high, so we have kind of high amount of epochs for 25. So I think we'll observe some overfitting, but let's see. Now let's try to test the model. So we'll do the testing part, and we are almost done with this lab. So with torch dot no grad, this is going to be to have total loss test is equal 0 and total accuracy test is equal 0. Then we will have for index comma input and label, so input comma labels in enumerate. So we're going to calculate, I don't think there is need for index here. I think that's not necessary. For in test loader, yeah, okay. Now we're going to do prediction is equal to model of input, and then we're going to have accuracy is equal to torch dot argmax of the same thing, so we can copy it easily. That's the one, but instead of having the that will be accuracy only, and that's it. Yes. Then we'll have total underscore accuracy underscore test is plus equal accuracy. We are calculating the accuracy now for each batch, and then we are adding it to the total accuracy here. So we will print, this should be outside the loop, we'll print total accuracy score is going to take the same thing we have here. This is to calculate the accuracy, but we will change some stuff here. So this will be total accuracy test, and this will be test dataset, and that's all. Let's see what it will give us. Okay, so we have an issue here. Yeah, this is not outputs, this should be prediction. Sorry, that's my fault. And we have the accuracy is 93%. So you can put it in a more fancy way if you want. So we can, I think that we should put dot item somewhere. I'm not sure, maybe here. No, not here, but we can fix it, but I think we can leave it for now so we don't complicate stuff. So the total accuracy score here, you can see it's 92%. So it's not bad, it's good accuracy. Let's see if we have any sort of overfitting. Still, accuracy could be good and we could have some overfitting, that's normal. I mean, if we avoid overfitting, we could get even better. But let's see if we have any overfitting first. Number of rows is 1 and number of columns is 2, because we will create a plot that is having 2 columns for validation loss and for train validation loss, train validation accuracy, but 1 row. Both are in 1 row. And we'll put figure size is equal to 15 by 5. Great. Then we will put axis of 0. So the first plot is going to be to have dot plot. This is going to have what? It will have the total underscore loss underscore train plot. You remember this is the list we created during before the training, and we'll give it a label, and the label is going to be training loss. Then we'll have axis of 0 is also going to be plot. So we'll plot inside the same axis total underscore loss also, but for validation, and we will label it validation loss. Then we will write axis of 0. We'll set some specs for this axis as set underscore set. So we'll have some details here. Title, we will give it a title, training and validation loss over epochs. Okay, then we will give it more details. So axis of 0, we will give it the x label and y label. So dot set underscore x label, and the x in this case is going to be the epochs, and we are going to take this for y, and we're going to set it as the loss. Also, I think that's all, but we will write axis of 0 dot legend for this axis. Okay, now we're gonna do somehow the same for axis of 1, but for accuracy. So we'll copy paste this, and let's make this 1 for all of them. Instead of loss, it will be accuracy, and instead of loss here will be accuracy and accuracy. Here instead of loss, we will also put accuracy, and here accuracy, and that's all. Now we will write plot.type layout, and then we are going to see our plot. Let's see. Okay, so n calls, this should be without underscores, number of columns, and great. Now it's not very clear, so we can set some limit or dimension limit. So for axis 1, we can set limits so that it can give us like some good view. Set underscore y limit. So the y limit for accuracy should be between 0 to 100, obviously, because it's a percentage. And we can set also some limit for the loss as well. So the loss for 0 should be between 0 to 2. Let's see. Okay, no, I think we don't need for loss. I think for loss we need also better range, because it's not very clear. So for loss, I think we can see here that accuracy is, for validation accuracy is a little bit low, and training accuracy is higher. So there is some sort of overfitting here. And we can see, we can remove the limit for the loss because it will be easier for us. So if you can see here inside the loss that it's not very clear, the overfitting is existing but not very clear as training. So you can see inside the training that the validation accuracy is lower than the training accuracy, but not by so much. So I mean, it's not very clear here, but still there is some sort of overfitting that can be improved further, but it's not affecting much the model, because you can see that the accuracy is 92% for the testing data, which is good. So that's all for this lab. This lab is complicated a little bit, and feel free to ask any questions in the comments. And don't forget to subscribe and like for more AI contents like this. If you have any ideas for future videos, feel free to share them in the comments as well. Thank you.